So let's consider an arbitrary network, right? So this is S and this is T, and there are some edges going here and there. I don't really know, but we don't really care that much, right? So there's a claim that's made in the slides that the max flow is not going to be large. It's going to be smaller than n times c, right? C is the max capacity of the edges, right? So basically that means that we want to give an upper bound, and the upper bound is n times c, where n is the number of nodes, right? Why is that, right? So what is the maximum amount of flow you can push out, right? So we can push out at most, right? At most, the number of flow is at most, right? Basically, you can really just imagine that if I look at all the outgoing edges like coming from S, right? So then if I just make all the outgoing edges saturated, right? Then we sort of can get an upper bound, right? It's at most, right? The out degree of S times C, right? So this will be a very conservative upper bound. The upper bound assumes that I'm somehow managed to be able to push maximum amount of flow along all the edges that's coming out of S, right? So it's in a lot of cases that simply is really just too much, right? So but it's really now the assumption we are making here is that what happens if we are just hitting the physical limit right around S, right? So the physical limits means that if there were only 3 edges that's coming out of S, and each edge can only carry C amount of C unit of flow, then basically means that there's no way I can push out 3 times C unit of flows out of S, right? So if I generalize this argument, then I can sort of give an upper bound on the maximum flow size, right? Which is the out degree of S times so basically out degree is the number of edges that's getting out of S, right? Times C. C would be the capacity limit for every single edge, right? So for every single edge, we are not going to be able to push more than C unit of flows out of the edge, right? So both of them are really just very conservative estimates, right? So after we take the product, right, we sort of also know that like what would be an upper bound on the number of outgoing edges, right? So this is really just that S cannot. This really means that it's at the worst, right? S can connect to everyone else, all other nodes, right? So that sort of means that the out degree of S cannot be larger than number of edges, right? Number of nodes, right? So basically, using this condition and then plot this condition back to what we are having here, then we get this is the value of the any flow cannot be larger than the number of nodes times C, which is n times C, and that's the reason the slide says that this is an upper bound. So let's switch back to the slide. Right, so now we are switching back to the slides, and then let me just erase a little bit, right? So we are seeing something here, right? So the value of the flow cannot be larger than n times C. And then we sort of argue that the number of iteration of the number of updates on the augmenting path cannot be larger than f star, right? So at the end, we know that the Fulkerson algorithm terminates with at most n times C round, right? So I think we sort of briefly mentioned the issue that if the running time is polynomial in C, this is actually not a polynomial algorithm, right? Because the polynomial algorithm's definition is it needs to be polynomial in the size of the input, right? C is not the size of the input, right? C is the max capacity, right? In order to describe an integer, right? In order to describe an integer between 0 and C, the amount of bits we need is log C, right? So that means that we need the algorithm to be polynomial in log C instead of C. If the running time is polynomial in C, it's actually not considered as an efficient algorithm. So that means that despite that, we do know that the running time has an upper bound because, right, so when we find the augmenting path, the amount of time we need is really n plus m, right, or sometimes we call v plus e, right? So this is the cost for running one augmenting path. And the number of augmenting paths we need is our n times c. That basically means that the total amount of the running time is m times n plus times c, right? But this is polynomial in m and c, but it's not polynomial of this in the size of the input, right? So we sort of hit this issue when we were talking about the knapsack problem, and we hit this back, and then so basically the corollary here says that it is indeed true that the algorithm can terminate, but at the same time, this is not an efficient algorithm. In case C is very large, this algorithm is actually very slow. So the next question is that theoretically it could be very slow. It can be as slow as m times n times c. But in practice, is it possible really to have a dependency that's really linear in C, making the algorithm very slow? And in fact, we can easily come up with an instance so that the Folkestone algorithm is going to be very slow if we do not impose further constraints on that, right? So this is actually the network we are an example of bad instance, right? So imagine that this is the source S and this is the destination of T, right? So we have a total number of 5 edges, right? So 4 of them has capacity C, and one of them has capacity 1, right? So if we look at this graph, right, it's pretty obvious that what's the optimum solution. Optimum solution basically looks like that, right? So I send the 2 flows along 2 passes, right? On each pass, the total amount of flow I'm going to send is C, right? So basically that means that the optimal solutions value is going to be 2C, right? So this is optimum solution. Now, the next thing we want to talk about is that what happens if we run for the Folkestone algorithm without imposing any constraint, right? Just the plain version of the Folkestone, right? So basically it says that there's no way that prevents us keep finding this kind of path, right? So imagine in the first round, we come up with this path, right? So we sort of see the bottleneck is 1, right? So in the first round, what we decide to do is to sort of update a flow so that it has 1 unit of flow walking along the path that's moving from S to V, from V to W, from W to T. Right. After the first round, let's see what do we get, like what kind of residual graph do we get, right? So we still have 4 nodes, right? So just for the sake of making for the sake of the better using of the time, I can directly draw out how the residual graph looks like. The residual graph looks like that, right? So right, C minus 1, C and C. Right, so there are something that's going back, but that's irrelevant, right? So the most important thing here is that we sort of notice that the edges that's connecting between V and W is flipped. Originally, it's moving from V to W, and after we use 1 unit of flow, then the edge is moving back to move. So the direction is flipping from V to W to W to V. Right. Under this graph, then we can sort of like find another augmenting path, right? So let's say that we are sort of unlucky, like our augmenting path is again moving from S to W, from W to V, from V to T, right? So in this case, then we sort of, let's say that we also add this additional augmenting path in the original graph. This is 1, and then this is another one that's going backward, and this is 1 here, right? So afterward, right? So if I integrate all the flow we have found so far, basically after the first 2 rounds, this is going to be the flow we have found so far. The 1 unit from here, 1 unit from here, 1 unit from here, 1 unit from here, right? So basically for the edges here, right? So originally there's a 1 unit flow from moving from left to right, but in the second round there's another unit of flow moving from right to left, so it's canceled out. At the end, we haven't basically it's effectively the same as we have not touched this edge, right? So this is the second round. In the third round, I can continue to get unlucky, right? So in the third round, so before we proceed of third round, let's also look into what the whole residual graph looks like, right? The edge is flipped again. Everything becomes C minus 1, C minus 1, C minus 1, right? The edge is flipped, right? So if you look at the edge is over here, right? It's flipped. back from left to right. But for the rest of them, not much has changed, right? Originally, everything is C. Now, everything is becomes C minus 1. Besides that, then not much has changed, right? So in this residual graph, we can continue to be unlucky and somehow decide to update along this direction, right? So basically, every round, if we don't impose any constraint, we have to. There's a chance that we always use the edge between U and U and W in every round. Sometimes it's from U to W, sometimes it's from W to U, but every single round we somehow have to touch the something in the middle. When we touch something in the middle, then our update speed will be very slow, right? So for this particular case, the total number of update is it's actually linear in C, right? So when C is large, a billion, then it's going to have a billion rounds of update, right? So let me just repeat what's being done here, right? So we are claiming that there could be a bad case, right? So we build out a bad instance such that if we run the very original version of the Ford-Foxson algorithm, the algorithm just pick up an arbitrary augmenting path. It's possible. We only say that it's possible that we can get into very bad situation in which the algorithm is going to take a linear in C amount of rounds in order to get the final solution, right? So the first statement here also re-emphasize that if the algorithm is polynomial in C, then it's not polynomial in the input size, right? So that's sort of the problem we are facing right now, that we sort of need to be able to find a way to improve the Ford-Foxson algorithm so that our algorithm will be much more efficient when we address when we tackle this setting here. So we only finished explaining why it could be why there could be scenario our algorithm can go wrong, and I feel that I need to spend around 20 more minutes in order to explain the how do we fix this problem, and we only have 10 minutes left, so maybe this time I will just cut this lecture short and put the explanation of the new algorithm for the next lecture, and maybe we will run a little bit over for the next lecture. Next lecture probably we will have somewhere between 80 and 90 minutes. So okay, so let's just wrap up today, and I know that your homework's assignment 3's deadline is approaching soon, so basically again, if you have any questions, just email me, Skype me, or just come to the office hours. Okay. Thank you for coming to the lecture again. So see you on